Okay, so here's what we were doing last time. We were doing this example of the multivariable chain rule. Real quick, let's rewind and remind ourselves what the multivariable chain rule is. It's this formula right here that basically says, as I have summarized below, differentiation turns a composition into a product. Honestly, it's pretty similar to single variable chain rule if you interpret it the right way. Namely, that the product is a product of matrices, because after all, that's what a derivative is. In a multivariable context, a derivative is a matrix, most fundamentally. Okay, so that in mind, we last time talked through much of this example where we had a couple of functions loosely described. I don't have formulas for them, right? And I was given, though, certain data about these functions, and the question was to use the given data to compute the derivative matrix of the composition at a particular point. And we talked through that, okay, well, by the chain rule, it's this matrix product here. And the matrices that we need are given, as it turns out, and you got to watch out for multiplying in the correct order and evaluating at the correct place, various details. And our punchline, though, was that derivative matrix is this. Okay, so that's where we left off. And notice, though, there is a second part to the question. Second part of the question says compute the partial of Z3 with respect to X1. So let's talk about how we would compute that. Let's first of all take stock on what do we have here. We've got this composition is a function that takes the X variables to the Z variables, right? And so let's see here. We have, we're taking the partial with respect to X1. We know that's going to be somewhere in this matrix, right? Being a partial with respect to X1, notice that X1 is the first of our input variables, and therefore we're going to be looking in the first column of our derivative matrix. Is everybody good? Remember, columns correspond to input variables. Partials with respect to input variables. Okay, next, notice we're taking the partial of Z3. Notice that Z3 is the third of our output variables. That means, keeping in mind that output variables correspond to rows, right? If we're looking at the third output variable, our answer must be in the third row. So altogether then, the thing that we're looking for, this partial derivative we're looking for is, well, it's got to be that entry right there, and therefore it's 3. Let me zoom in a little bit more. We can see a little bit better. There we go. Okay, does everybody follow? Everybody with me? Okay, so moving along then. There we go. Okay, so there's a couple of special cases I want to talk about. I'm going to talk about these pretty quickly because there's nothing that exciting happening here, but I do think it's worth pointing out. Let's consider first the special case of when we have just a single input variable to our first function in the composition. Right, so R1 starting us off there. Well, if you think about it, what that means is that this function here is position as a function of one variable. It means that that first function is a parametric curve, and its derivative matrix, since there's only one input variable, there is only one column. In fact, that is our velocity of this, which you might call input parametric curve. Okay, now let's think about the composition. The composition, also a function of just the one variable. Just one variable means that there's going to be, again, just one column in the derivative matrix of that composition. And so again, that means that we're talking about a velocity vector, this time of that second parametric curve. Right? So what this does then, if you ask, well, what does the chain rule say? The chain rule is, in some sense, telling me about this function f. It's telling me about the second function. It's telling me about a relationship then between the input velocity to this purple function and then the output velocity from this purple function. This is something we already knew, but nevertheless I do think it's kind of cool that this restates this known interpretation that what a derivative matrix does is it relates input velocities to output velocities. And a point of view you can take is that this statement about derivatives relating input velocities to output velocities could be viewed as, depending on the approach you take to these things, could be viewed as a consequence of the chain rule. In this special case where you have just the one input variable. Okay, all right, so I just think that's worth an acknowledgement. Here's an example. So you'll notice here I have a function f and formula up here for this function f. Fine, whatever. And then you'll notice also that there's some discussion about movement. That I've got a certain velocity here in the domain, and there's a resulting velocity that I want to find in the target. And input velocity, output velocity. So that means that I'm moving in the domain. Then there's an image moving around in the target, and you can think of those as parametric curves, and you could think of this as being part of a kind of a chain rule situation where all of these are functions of t. Right? We've got a composition. This dependence on t gives me a parametric curve in the x space. The composition gives me a parametric curve in the, what you might call the y space. So, using the interpretation from the previous page, not that we really need to, we already knew that derivative matrices relate input velocities to output velocities. But anyway, using that interpretation, wherever you view it as coming from, you can compute the derivative matrix of f. We've got the actual formula for f, and then you can plug in the point in question. Don't forget our point in question. Here, let me do it like this. Our point in question is 2, 1. So plugging in 2, 1 gets me to this. And that's our derivative matrix. That's what we multiply by our input velocity that was given as 4, 3 to get our output velocity that we're looking for, which ends up being that. Okay, so chain rule, basic interpretation of the derivative matrix, take your pick. Either way. All right, another special case, and again, I don't want to get too bogged down in these special cases because they're just kind of repeats of things we've already said. Still looking at only one input variable in our original sort of domain of our first function in our composition. Now suppose further that there is also just a single output in our second function. Right? And how does that change things? Well, by virtue of there being a single output to this function, that means that this derivative matrix, you think about it, always keep in mind, if you're talking about a function, you want to write the derivative matrix. Columns correspond to input variables. Rows correspond to output variables. So if you only have one output variable for this f function, one output variable means this matrix is just going to have just the one row. Right? And it remains still that because there was just one input variable way back here, it remains that there's just the one column there, and of course also just the one column here, but now also just the one row there. And so altogether what we have is that the composition is a plain old single variable function. One output y, function of one input t. So the derivative matrix of the composition is just a single variable calc 1 derivative, dy dt. And these matrices on the right have turned into, well, a single row matrix and a single column matrix, and this multiplication could be reconceived of as a dot product. Right? This is an alternative interpretation of matrix vector multiplication. When there's just the one row, think of it as just the gradient vector. And again, we've already seen the gradient vector. We've already seen that when you have a derivative matrix with just one row, it's morally equivalent to there being a gradient. Nothing new here. Just want to point out what the chain rule looks like in this context. When you have just the one input and just the one output, the chain rule becomes old news, a different piece of old news about gradients relating input velocities and output, what you might call rates of change, I guess, because it's just scalar valued. So again, example. Suppose you've got a bird flying around in space, and we've got a temperature function in space. Right, so the bird movement means that for every value of t, I get a corresponding position, and then this temperature function takes that position and gives me an output, namely the temperature. So we have a composition of functions. Again, we're trying to find the derivative of that composition, the rate of change of the eventual output with respect to the original input. Right? And our formula tells us that that's computed with, again, dot product with the gradient. So we're going to take our temperature function here, compute its gradient, plug in the point in question, etc. And knowing that gradient, we dot it with our input velocity, which was given to be 201. And again, arithmetic and answer. So again, nothing new. All right, we've done stuff like this in the past. Again, it's just a basic interpretation of the gradient. Or is it an alternative sort of special case interpretation of the chain rule? Kind of take your pick. Alrighty. Okay, so now to a new point of view on the chain rule. I deliberately start with this point of view here about composing functions and thinking about velocities, input velocities and output velocities, because ultimately I think this is the simplest point of view. It may be a little bit sophisticated, it may be a little bit unfamiliar, but it's ultimately very simple that just input changes, output changes. When you do it twice, you're doing two matrices. There's, in some sense, not a whole lot not a whole lot of machinery to go into developing this. We got a composition of two functions and product of the corresponding derivative matrices. So I believe in starting with this first. Ultimately, this is the right way to think about the chain rule. But now let's look at a different point of view, and this different point of view is going to be nice in some other different special cases. So, old news. If you have a first function, f, where the y's are the functions of the x's, then we can write down its derivative matrix. Again, first function means it's the first matrix, which means it's on the right, not the left. Keep that in mind. Right? Then we've got a second function, which takes the outputs from the first function as its inputs. So again, it's a composition that we're looking at here. And then we're going to get a new set of variables z's that are functions of those y's, and that gives me a derivative matrix. Second function gives me the oh gosh, what did I do? How did I write a 2 here? I was thinking 1 as I wrote this. Sorry about that. This is a 1 right here. This is the first matrix because it's on the right. Did I step on my own landmine there? I may have. So first matrix is on the right, second matrix is on the left. Okay, so there's the chain rule that the derivative of the product, giving the z's as functions of the x's, and therefore with derivative matrix this, is the product of these first two. Okay, everybody with me so far? This is just setup, right? I'm setting up a collection of variables. Okay. What if I actually don't need to know this entire matrix? What if I just really, honestly, I just want this one entry. I don't really care about the other entries. This is all I want. It's all I need for whatever reason. And very often this is the case. I just want the one entry. Why write down all of this stuff over here? I'm never going to use any of that in the computation of that purple entry. I'm not going to need any of that stuff there. And likewise, I'm not going to use any of this over here, nor any of this over there. So why bother writing it down, computing those partials? Why bother multiplying the whole matrices to get this whole matrix? It's a lot of work. right? And it's much easier to just remember that that one entry we want is this row dot that column. And that dot product is pretty easy to write down. There's the entries from the green row. Here's the entries from the blue column. And the dot product is that. Everybody with me? Okay. All right. Now, so this is an alternative point of view on the chain rule, and it's perfectly fine, I suppose, to think of the chain rule this way. Pros and cons. Again, if you only need the one entry, then this is a pretty good formula to have, pat down, ready to go, plug and chug. It's very kind of lean in some sense. But it is also kind of inelegant, really. And it's not as elegant, it's not as easy to motivate, I would argue, as this point of view right here is, again, a little bit unfamiliar looking, but makes it really easy to motivate a powerful conclusion with a tremendous amount of information in it, all with one picture. So, pros and cons. So I'll say this is a good supplemental formula to know for the chain rule. Okay, now before we get into an example, I do want to give you a warning. A lot of students misunderstand this. And maybe perhaps start writing it down and say, okay, this partial derivative, well, here's the first term. And then they think to themselves, hey, wait a minute, let me pause there for a second. Doesn't that and that, don't those cancel? And doesn't that leave me with the partial of zi with respect to xj? Aren't we done at that point already? And can't I therefore just ignore all the rest of these terms? Seems pretty tempting, right? It looks like it, at least from a notational standpoint, kind of looks like it ought to work. And this is dramatically wrong. So, for one thing, we know it's wrong because it's in conflict with the answer that we know is right. We know this has got to be right because that's what came out of this established formula that we already know. And so it can't be right. Let's talk, though, about why it's not right. Why can't you just cancel those, seemingly, a factor from the numerator, a factor from the denominator? Why can't I just cancel? Well, it's ultimately the fault of the notation. The notation that I have here, for example, makes it look like there's this independently well-defined thing called partial zi that always means the same thing in every context, and it just is what it is. And that in the denominator we have this independently well-defined thing called partial y1 that exists by itself independent of other things, and it's always the same thing. And that's just not true. These are not independently existing things. This notation here is basically saying, well, there's a particular scenario. There's a particular scenario we're describing, and in that scenario, with certain very important choices having been made and set, in that scenario, then we're going to look at things that we could reasonably denote with these things and divide them. Yes, that's true. But importantly, these are different scenarios. Let's take them one at a time. What's the story here? What's going on in this picture? In this picture, we're taking a partial with respect to y1. Don't forget what partial means. Partial means I'm going to hold all the other variables constant. Right? So zi is a function of a bunch of different y variables, y1 through ym. I hold all of them constant except for y1. And in that scenario, I ask, okay, when I change y1, how much does zi change? Okay. Fine. Now let's look at this thing over here. What's the story? Where does this come from? What is the scenario in which this makes sense? The scenario is that we are going to, again, it's a partial derivative, so I'm going to hold a bunch of things constant. Xj is going to be my variable. All of the other x variables will be held constant. And if all those other x variables are held constant, but if xj is changing, then all the y variables are going to be changing. The y variables depend on xj. You change xj, you're going to change all of the y variables. And so in this setting, in this scenario, the y variables are not constant. Right, so very importantly, see, we have a kind of a disconnect here between these scenarios. These are completely incompatible scenarios. In this scenario over here, where we're dividing this by that, the y variables are not constant. In this scenario over here, where we seem to be dividing this by that, totally different scenario. The other y variables are constant. So two different stories, two different calculations, you might say, right? And so point being that these things, this thing here and this thing here, they're just not the same. Any more than if you were, imagine you're taking a test and question number 1 on the test has, there's some given algebra and there's a relationship between x, y, and z and you compute some stuff, whatever. And then next page, question 2, there's completely different algebra relating also x, y, and z. You can't use what you know about x from the first question in your solution to the second question. They're totally different questions. These x's don't have anything to do with each other. And likewise, these partial y1, this partial y1. They're participants that play kind of similar roles, but in totally separate scenarios, and you just can't compare them. So there is no cancellation. Does that make sense to everybody? I hope. Heads up, just to make sure, you got to watch out for that. It is extremely tempting, and it used to be more common than it is now, because I've been hitting this point pretty hard for the last few years. But it used to be a lot of students would write down this with that cancellation in mind, completely then forgetting about all of these terms, and their answers, of course, are unsurprisingly wildly wrong. And worse than that, their reasoning is wrong. So anyway, don't make that mistake. Don't step on that landmine. Okay. All right. So let me give you an interpretation of this equation. This, again, is our revised chain rule, right? Our sort of alternative form of the chain rule. This interpretation I'm about to show you is good intuition for this, but it's also a good sort of computational perspective. We're going to be using the following not just for intuition purposes, but for computational purposes. So this is something that you need to think about from a computational point of view. We have a bunch of x variables, a bunch of y variables, a bunch of z variables, related by these two functions. I can get this to erase, right? We have this gives those is my first function, and then we have these give those as our second function, and then the composition and all that. If I want to compute a partial of zi, there it is in this diagram. Partial with respect to xj, there it is. Being a partial derivative, don't forget that means that all these other x variables are to be held constant. So those are all constants, those are all constants. So that's our scenario. And now let's just kind of think through what happens, right? When I'm holding all these x variables constant except for xj, if I start to change xj a little bit, what happens? Well, if you change xj, y1 is going to change. And if y1 changes, that mere fact alone will cause a change in zi. So this is what I'm going to call a propagation of change along a path. Along that path there, a change in xj causes a change in y1. A change in y1 causes a change in zi. Okay. And then there is a propagation of change along a separate path simultaneously with what we just observed. As you change xj, that will also change y2. That change in y2 will also contribute to a change in zi. Right, that's in parallel. And then likewise, the next path and the next path and etc. all the way down to this last path. Change in xj will cause a change in ym. Change in ym will contribute to a change in zi. So for each one of these paths, you get what I'm going to call a term in the total formula for how, what the relationship is between xj changes and zi changes. Okay, now let's think about what these terms ought to be. What is this term? As I change xj, for example, how much change does that cause in y1? We have a multiplicative factor, right? The relationship between changes to an input variable and changes to an output variable. That's what a partial derivative is. So this factor right here, partial y1, partial xj, this factor is in recognition that however much xj changes, y1 is going to change by that factor more, or proportionally by this factor. Not necessarily more, but you know what I mean. And then furthermore, as y1 changes, how much does that contribute to a change in zi? Well, again, with the partial derivatives. And so this separate factor here, partial zi with respect to y1, that represents the sort of the amplification of the change in the second step along that path. And so altogether, a succession of factors is a factor by the product. And so altogether, over the entire path, you get that term. What do you think? You buy it? Everybody happy? Okay, so ditto for the other paths. And then finally there is a last path that gives rise to this last term. Notice that there is for each one of these paths, there is a corresponding intermediate variable, what we call an intermediate variable. Y1 is kind of in between the xj and the z. Right? So we can think in terms of paths, or you can instead just think in terms of intermediate variables. They're kind of interchangeable. And then furthermore, notice, whichever variable is your intermediate variable shows up the same way every term as kind of a denominator and numerator. It's the things that we had this temptation to want to cancel. Right? That's just where they show up. And then likewise down here, this intermediate variable, ym, again, sort of denominator and numerator like that. And this is always partial zi, and this is always partial xj. So it's a really nice pattern. These terms correspond to paths. The paths correspond to intermediate variables. So this is what we call sort of the intermediate variable point of view on a composition on the chain rule. Okay. All right. So why would one go to all this trouble? Well, again, it beats the alternative in a lot of cases. So let's look at this one here, for example. Suppose I've got this function composed with this function, and now do be very careful. You got to make sure to which one plugs into which one, right? Always think about the order. And it seems that what comes out of F is what's going in to G, and that means that F acts first, right? And then G here acts second. And altogether, you can see on this little diagram I've got here, all of the outputs of F, all of the inputs of F, here they are in the little green box, all of the outputs of Z, all the outputs of G, all the inputs of G in this little blue box here, and the outputs from the first are the inputs from the second, as is required if you're doing a composition. Okay. All right. So I can now just look at this at this little diagram and answer the question that's been asked. Here's the question. I want to compute the partial of Z2. Hang on, Z2. There's Z2 on our diagram. I want to compute the partial with respect to X2. X2. My stylus is getting old and worn, and it's not working as well as it ought to. There's X2. So the partial I've been asked, I can see right here on the diagram what's the input, what's the output, and then furthermore, I can see what are the paths, or said differently, what are the corresponding intermediate variables. My intermediate variables are y1 and y2. And so then correspondingly, for this y1 path, I get a y1 term. And likewise, for this y2 intermediate variable, aka y2 path, I get this y2 term. And there's my chain rule as applied to computing that one partial derivative. I don't have to compute two entire matrices of partial derivatives. I just need these ones specifically. Okay. All right. So a little bit of computation follows. Let's just do one of these. What is the partial of Z2 with respect to Y1? Well, let's see. There's Z2. It's Y1 cubed. It's just a given. That's the given formula. What is its partial with respect to Y1? Well, the partial with respect to Y1 gives me 3Y1 squared. Just a partial derivative. Nothing tricky there. Likewise for the other partials. Everybody all right? Okay. So a couple of heads ups. Let's start with confusion of variables. I like to segue into this by doing a single variable calculus example because this problem does exist in single variable calculus. It's just that there's so little else happening in single variable calculus, it's not hard to just remember and pay attention to this point. So I'm going to do a computation now of a single variable calculus question 3 different ways. I'm going to start with doing it the wrong way, a wrong way. Of course, there's lots of wrong ways, right? But I'm going to do it a wrong way by being a little too fast and loose with my interpretation of the chain rule and just saying, look, the derivative of composition is the product of the derivatives and, little slapdash here. But having done that, I mean, the derivative of g, I would be forgiven for writing that as 3x squared based on what I have here. Right? And let's see, f prime, well, here's f, and that's 2x, and altogether it really looks like this ought to be 6x cubed, which of course we know is wrong. Okay, now let's fix it. The mistake, of course, was that when I wrote down g prime, I should have written g prime evaluated at f of x. That's the deal, right? G is not being evaluated at x. It's being evaluated at f of x because we're composing, right? And so with that in mind, g prime still is 3 times whatever is on the inside squared. It's just that now what's on the inside is f of x, aka x squared. And so I get 3x squared squared. Not 3x squared. So, yeah. And then ditto for the rest of the problem. And here we get a correct answer. Now, to be totally honest, though, you notice I wrote this as valid. I didn't write this as, good, because I still honestly don't like how this got written down. Let me show you what I think is the much better way to do this question. As soon as you see that you're composing functions, you should be thinking in terms of pictures like this. You should be thinking in terms of, slow down. We're composing functions? Oh my, okay, well, then I got to make sure that what comes out of the first function is the same as what goes in to the second function. That's, after all, what a composition is. And that kind of forces our hand on one thing. In particular, the thing that comes out of f, I can't call this x That'd be ridiculous. X is the input for f. It can't also be the output from f. So if I don't call it x, if I call it, for example, y, whatever comes out of the first one has to be what goes into the second one. What that tells me is I really should rewrite this function g in terms of a new dummy variable. I should rewrite g in terms of y. And you'll see that's what I've done here. I've written g as a function of y. Now that's morally the same function as what I have up here. Whatever you give me, I'm going to cube it. Whatever you give me, I'm going to cube it. I mean, it's the same statement, just I'm renaming the whatever you're going to give me. Right? It's what we call a dummy variable. Right? It's just a placeholder. And so don't use the wrong placeholder to make a confusion of variables problem with your composition. So just rewrite that second function, avoid the confusion of variables, and then look how easy the chain rule problem is. Go ahead and be fast and loose with the chain rule. It's fine. Derivative of composition is the product of the derivatives. Cool. Yeah, whatever. We don't even have to worry about this whole where are we going to evaluate it business. G prime, 3y squared. Notice y, because its function is written in terms of y. Let's see here. F prime is 2x. Cool, you multiply it out, you get this, and then you realize, I've got an answer here in terms of two variables, but the composition that I'm interested in, this composition whose derivative I want to compute, is a function of just x. So I need to rewrite, if the composition is a function of just x, I need to write its derivative in terms of just x. And so wait a second, what is this other thing here? I've got a y there. That shouldn't be there. I need my answer to be just in terms of x. So how am I going to rewrite y in terms of x? Oh, right. Y, the thing that goes into g, is the thing that comes out of f, namely it's x squared. Let's see here. Anyway, this going into there for y, and your final answer then is, again, correct. So I think this is much better. I would much rather do this than this, because there is something just intrinsically confusing, thus the name confusion of variables, right? So I would rather just not commit confusion of variables in the first place, as opposed to dealing with confusion of variables in a confusing way. Okay, so now single variable calculus discussion behind us. Let's observe we can do the same thing in multivariable. Right? Now here there is a lot more going on. We're writing down matrices. We're doing matrix algebra. Like I say, a lot more happening. So it'd be a lot easier to accidentally kind of forget about this whole confusion of variables thing. So here you go. When the question says you want to compose, or if you find yourself in a circumstance where you're composing functions, right, like so, get your variables straight. If f is going to be a function of x and y, then the outputs cannot be called x and y. They have to be called something else, let's say u and v. And wait, if the outputs from f are going to be u and v, that means the inputs to g need to also be u and v. So I've got to rewrite my g just in terms of these new dummy variables, u and v. So everywhere I see an x, I'm going to put a u, and everywhere I see a y, I'm going to put a v, and just, find and replace. Nothing happened here. These are the same function, just written with respect to different dummy variables. Okay. And with that done, we're all clear, free and clear, no problem. There's no confusion of variables here. The outputs from f are the inputs to g, and we're in business. And so let's see, derivative matrix for f, derivative matrix for g. I can multiply them. Notice, I'm not being careful about where I'm evaluating what. I don't need to be. The fact that I've named these variables carefully will keep track of that for me. right? Having avoided confusion of variables, the bookkeeping is automatic in some sense. So then, you write down these matrices. Now notice the little dirty trick I pulled here. Again, the matrix that is on the right, aka first in the matrix product, I wrote that on the left. Which, coin flip about half the time in real life that will happen, right? So do be careful. Make sure to multiply the matrices in the correct order. First means matrix on the right. Because that's the first function acting. And then let's see, second function. Here's its derivative matrix. It's on the left. And off you go. Boom. And multiply them out. Oh, and then before or after, doesn't matter. But I'm going to go ahead and do it here. Before I multiply, let's get rid of this u. My answer needs to be in terms of x and y. The composition's a function of x and y. I need my derivative to be in terms of x and y. What's this u doing here? Oh yeah, u is the first input to the g function. So it's the first output from the f function, and so u is x squared plus y squared. And I'll substitute that accordingly. And likewise for the v, and then use multiply. Everybody okay? Okay. All right, next warning. When we compose functions, you can make a little diagram relating variables like this. That does not mean that any diagram that you write that relates variables can be instantly and as is interpreted as a composition of functions. There are weirder diagrams, such as what I have drawn here, that this is not as written. It's just not a composition of functions. And notice that our chain rule, everything we've written about the chain rule comes out of literally composing functions. Right? We composed these vector-valued functions. We got a fact about derivative matrices. We interpreted that, and everything came out of that. So I've got to make sure that my diagram actually does represent a composition of functions. And so that means several things. I need to know exactly what my inputs and outputs are for these functions. And the inputs all have to be independent of each other. That's the deal with functions. And they have to fit together as Legos should. That the outputs from the first function, it's got to be a perfect match to the inputs from the next function. That's how you compose functions. So you can see that all happening here, right? Here's my first function. Maybe I call that f. Here's my second function. Maybe I call that g. And check it out. The outputs from f are the inputs from g, et cetera, et cetera. So we're all good in this diagram on the left. On the right, what's going on here? This is a mess. I don't know what's going on there. I suppose you could kind of say, these variables are functions of those variables. But then look at the problem I end up with. What are these variables functions of? The z's, z1 and z2, they're not just functions of the y's. They're not. Z1 depends also on x1. So, the outputs from the green function just aren't exactly equal to the inputs from the purple function as I'm trying to, I'm trying to make it fit with all these requirements. You can't. It doesn't work. So this is a mess. For example, let's ask the seemingly innocent question of what is this thing, partial of z1 with respect to x1. Okay, well, slowly and carefully, here's, colors. Z1 is there. We're going to take the partial with respect to x1. Okay, well, there's x1, and don't forget, these are functions of these, I guess. right? And so if I'm going to take a partial with respect to x1, that means that y1 and y2 should have to be held constant. But again, you can't. If x1 is changing, and I'm interested in how that affects z1, unavoidably, x1 changing will also cause y1 to change. I can't say change x1 but don't change y1. Doesn't make any sense. Is everybody with me? So this is just a mess. This is not something that we can work with the chain rule. Our chain rule requires composition of functions. Well-defined functions, well-defined composition. So here's how you fix it. The fix is to redraw that diagram as follows. This kind of, if you will, line right here, the problem is it's kind of jumping over that second level, is jumping over the y's and going straight to the z's, and it's just not good. So, well, let's put another variable in there. Let's insert, and let me zoom so we can see better. Let's insert this x1 star. It's just x1. Its value is always the same as the value of x1. It's a function of x1. The formula is x1, right? But notice now everything's kind of straightened out. And now, with all of this in mind, I've got a first function here. I've got a second function here. The outputs from the first or the inputs from the second. Everything fits and everything's fine and we're good. And all we have to do is just kind of rewrite everything that we have with this thing in mind. So now, in particular, let's come back up to here for a second, and let's imagine that we were tempted to wrong color. That we were tempted to draw this diagram with this set of equations in mind, and these equations down here. This kind of thing will happen in everyday circumstances where y1 is a function of x1 and x2. So is y2. Z1 is this formula, Z2 is this formula, and if you draw that all out, what you get is this diagram, which we've just agreed is a nightmare of problem. Right? So we fix it. We've already fixed it, in fact, by this down here. Notice then that Z1, previously thought of as x1 plus y1 plus y2, no longer, I fixed that by making it x1 star plus y1 plus y2. Now I've got, as required, z1 as a function of just the variables where it's supposed to be a function of. And we're back in business. So again, our revised situation is we have our updated diagram. We rewrite that equation like this. These other equations were all fine. We keep them as they are. And we've now taken the awkwardly phrased question that we were given and rewritten it in a way that now there's no issues. Now we're looking at a composition. Now we can make sense out of everything. And let's ask the same question that was a tragedy above. What is the partial of z1 with respect to x1? Well, z1 is here. x1 is here. No sweat. I've got 3 intermediate variables. Therefore, 3 terms. 1 for each of my intermediate variables. Nothing to it. And by the way, some of this simplifies actually pretty nicely in the sense that let's look at this one right here, partial of x1 star with respect to x1. That's that partial right there. Oh, well, it's the world's easiest partial derivative. The partial of this thing, aka this, with respect to x1, it's just 1. So this is just a factor of 1 right there. And factors of 1 you can just drop. And off we go. Everybody okay? So heads up, be careful, make sure that if you have a collection of equations given to you, make sure you interpret the given equations as a composition of functions in a legitimate way, and don't write down a bunch of garbage like this. And I guess we're out of time, so we'll draw the line right there. Real quick, let me comment. Don't forget we have an exam on Friday. And let's see here. Today's material, not fair game for the exam. Y'all will recall the color coding that we have here. Right? Oh, gosh. So the green coloring is the indication of what is fair game for exam 1. And notice that today, Wednesday, Feb 8, is in yellow. Right? So today's material, not fair game for Friday's exam. But it is fair game for exam 2. If I can get this thing to move, here we go. It is fair game for exam 2, which you see is not that long from now. It's like a little over a month. Right? So anyway, for your consideration. But good luck on the exam on Friday. See y'all then.